Section 3.3, we're now going to take derivatives of both log and exponential functions. So basically we're just adding to the tool belt the derivatives that we can take, so we've got more types of functions to find their rate of change. Let's go ahead and start with an exponential function. The most basic formula is that if we have an exponential function, and we're not going to worry about it being ab to the x, let's just worry about the exponential piece. The derivative of that function is to copy the question completely and then take the natural log of just the base. And it may seem odd, but you can go through the derivation to figure that out. Now, what's going to happen though is often we're going to have a little bit more complex equation than just a single x. Perhaps we'll have u, which the exponent's more than x, it's a function of x. So we're still going to copy the question identically. We're still going to take the natural log of whatever that base is, but since u is more complex, we need to now take the derivative of that complex exponent. You could argue we were doing the same thing in the problem above, where the derivative of x is just 1. So multiplying the above formula with 1 didn't actually look any different. Now keep in mind there is a special case because both formulas use the natural log. What if our base was e? What happens is we would still copy the question. But when it comes to the natural log of the base, in this case, our base is just e. So we would be taking the natural log of e, but that can be simplified to 1. So we don't need to say times 1. Same thing down below. We're going to copy the question, but the natural log of e is going to be this invisible 1, where we just need to worry about taking the derivative of the exponent. So let's go ahead and look at some examples. Find the derivative of 7e to the power of 4t plus 1. Our input is t, and t appears in the exponent. So I'm going to leave the 7 out front of my derivative as a coefficient. I'm going to copy the question. I don't need to take a derivative, or I don't need to include the natural log of the base because our base is e and that would simplify to 1. But I do need to take the derivative of the top, this du dx portion, which is 4, and then I can go ahead and multiply the 4 and the 7 to get 28 in front of the question. Same thing over here. I've got x as a variable. X is multiplied with the 5, which is multiplied with the cosine of x. They're separated by a product, so I'm going to need the product rule when I take the derivative of the numerator. I went ahead and thought of f as 5x. You could have left the 5 out as a coefficient like we did with the 7 on the previous problem, but g is going to be the cosine of x. And for ease, I decided to take their derivatives off to the side. So taking the derivative of the u function, where my variable is in the exponent, step 1, I copy the question. I don't need to take the natural log of the base because the base is e, but I do need to take the derivative of the exponent. For us, that's going to be a product rule of f prime times g. Here's my f prime, here is my g. We always add for a product rule, and then the formula is g prime times f. So our g prime and our f are put on the right side of the plus sign. Nothing to simplify with the exponential piece, but in terms of the right side, we do tend to put the 5x in front of trigonometric functions, and we don't really want to write plus a minus sign, so we just wrote minus. Notice these parentheses are crucial so that the exponent is technically multiplied with both terms of the product rule. Moving along with log functions. If you ever have log base b of x as your function, then your derivative is to write 1 over the variable piece times the natural log of the base. And that may seem awkward because here we have log, not natural log. So this one is, log base e. But whatever the base of the original log is becomes the base of the natural log in the derivative. And again, what if it's not just the log of x? What if it's something a little bit more complex than x? For example, a function u, which we think of as u is some function in terms of x. So again, I'm going to have 1 over the variable, whatever that variable may be. I'm still going to take the natural log of the base. But now we have to account for the fact that this variable was a little more complex. So I need to take the derivative of the variable. And again, what if you originally had, I wrote that horribly, What if you had ln, which is log base e, right? So when I come to the part where I need to add ln of b to the denominator of the derivative, I don't need it because the ln of e equals 1. So same thing, I get to get rid of that tiny little piece in the derivative only when the original function is a natural log. So I'm asked to find the derivative. I've got x more than once in my function and they're separated by a times. So I'm going to need a product rule. So I'm thinking of f as the natural log of 5. We just said for the derivative, we're going to take the variable, which in this case is 5x, and put it in the denominator. I don't need ln of e because that would just be 1, but I do need to take the derivative of the variable, which is 5. And once I simplify this, it simplifies to 1 over x. When I go to take the derivative of the cosine of x cubed, I know the derivative of the cosine is negative the sine. Whatever the variable was stays the same, but in the event that it's not just x, in our case it's x cubed, I also need to take the derivative of that variable to be 3x squared. So we're going to go ahead and stick that 3x squared out front. So taking the product rule for the derivative, I have f prime, which we found to be 1 over x, times the original g, cosine of x cubed. We always add for a product rule, g prime, which I already found, times f, which came in the original question. And in terms of simplifying here, technically this was cosine over 1, so I can rewrite this where I have cosine over x. Keep in mind, I cannot cancel these because it's cosine of something. It's not cosine times x cubed where I could simplify. We don't want to write plus a negative, so we added it to subtraction. And I went ahead and left everything else in that order, but it could be rearranged. Okay, last problem. The key here is my function is inside of a radical. So I don't need a product rule, but I am going to need a chain rule because I'm going to think of what's inside the radical as being to the 1/2 power. So using a chain rule derivative function, I'm going to move that 1/2 out front. I'm going to subtract denominator over denominator to get negative 1/2 as an exponent. And I leave the inside identically alone, identically the same. But now I need to go ahead and take the derivative of that inside. Because it's a natural log, I take the variable and put it in the denominator. I don't need an ln of e because it's base e. But I do need to take the derivative of the variable. So for us, the 3x squared minus 5. Now in terms of simplifying this, I tried to use color to our advantage. I left the 1/2 out front. I took the derivative of the natural log in purple and moved it over to the side. And when I took the derivative of the variable itself from that denominator, I went ahead and put it over 1 just for scale perspective. And then when I took the long term to the negative 1/2 power, I remind you that it was originally over 1, so it needs to go to the denominator. So my numerator is the only thing that stays there, my binomial. In the denominator, I'm going to go ahead and leave the factored form of my first 2 terms with the 1/2 piece that went to the denominator.